Let me start the module 4. Module 4 containing magnetic forces, materials and inductance. Okay, three parameters are there. So we have to deal with the magnetic forces, magnetic material and magnetic inductance. Okay, so force on a moving charge. Okay, first parameter is what is actually force with respect to moving charge. In an electric field, the definition of electric field intensity shows as a force on a charged particle. Okay, so with respect to electric field, we have seen force also, and we have seen what is actually W, work done, is equal to. Okay, so force is equal to what? Force is equal to Q into E. Okay, force is equal to F is equal to Q into E. E is the electric field, and Q is nothing but a charge containing a which charge is moving. The force is in the same direction as the electric field intensity and is directly proportional to both E and Q. So F is directly proportional to both E and Q element. A charged particle in motion in a magnetic field of a flux density B. Okay, we are indicating flux density, that is what B. Okay, we are indicating flux density, that is what B. Flux density as B is found experimental to experience a force whose magnitude is proportional to the product of magnitudes of the charge Q. Okay, so is found experimentally to experience a force whose magnitude is proportional to product of magnitude of charge Q, its velocity V. Okay, so magnetic field, whatever the its density, flux density is B, and its velocity is V, and flux density already we have discussed, that's what B. The sign of the angle between the vectors V and B. Okay, the direction of the force perpendicular to both V and B is given in with respect to vector Q into V cross B. Q into V cross B. That's what you can indicate with respect to electric field intensity. F is equal to Q into E. We are indicating. Okay, you can see here we are indicating Q and E. Okay, here we are indicating Q. E is nothing but V cross B. E is nothing but V cross B. V is a velocity and B is a flux density with respect to magnetic field. So this is what the equation it is indicating for the magnetic field. This is what the equation it is indicating for the magnetic field. For the magnetic field, F is equal to Q into V cross B. Okay. A fundamental difference in the effect of electric and magnetic field on a charged particle is for a force which is always applied in a direction right angle to the direction in which particle is proceeding can never change the magnitude of the particle velocity. Okay. In other words, the acceleration vector is always normal to the velocity vector. The kinetic energy of the particle remains unchanged and it follows the steady magnetic field, is incapable of transforming energy to the moving charge. Okay. The electric field on the other hand exerts a force on a particle which is independent of the direction. So with respect to the magnetic field, we have to consider the direction, and with respect to electric field, irrespective of the direction, the force will be there. It is the same. Okay, it is the same. That's what it is indicating, which is independent of the direction in which the particle is progressing, and therefore effects on an energy transfer between field and particle in general. The force on a moving particle arising from combined electric and magnetic field is obtained easily by superposition. Okay, so this is what we are indicating. So this is about one force with respect to electric field. Okay, one is with respect to electric field and another one is with respect to magnetic field. So if I consider the force because of both electric field and magnetic field, if you consider the force because of electric field and magnetic field together, what is actually force F is equal to, what is actually F is equal to, so F is equal to Q into E with respect to electric charge, F is equal to Q into V cross B, it is with respect to magnetic field. So if you combine both the equation, what is actually F is equal to, if both magnetic field is there and electric field is there, so in that condition what is actually force we are indicating here, F is equal to Q into E plus V cross B. Q into E plus V cross B. That's what first equation is, Q into E. Okay, this is with respect to electric field intensity plus plus with respect to magnetic field intensity. So this what Q bracket V cross B. We are indicating V cross B. This is for the magnetic field. This is for the magnetic field. So together we are adding these two because of electric field plus magnetic field. So we are getting total force is equal to. This force is given as a Lorentz force equation. Okay, this force is called as a Lorentz force equation. Lorentz force equation. So this is about the force due to magnetic field and electric field. So here you have to remember the three equation. First one we have seen already with respect to what is the magnetic field. Sorry, what is the force due to electric field? Second equation, what is the force due to magnetic field? Third equation, together due to magnetic field and electric field together, what is actually force? So that is called as the Lorentz force equation. That is called as the Lorentz force equation. Okay, this is what the third equation you have to remember. So force on a differential current element. Okay, we are indicating now with respect to small elemental length, what is actually force we are indicating here. Okay, what is the force due to small elemental length? Okay, the small charge is there. Okay, the force on a charged particle moving through a steady magnetic field. Okay, we are considering a steady magnetic field. What is actually steady magnetic field? It will be not varying with respect to distance. Okay, it will be same. Whatever the field is there, it is same everywhere. May be written as differential force exerted on a differential element charge. Okay, differential force it is given by df and differential charge it is given by dq. So remaining element it is v cross b. So only what we have changed is whatever we are writing f is equal to q into v cross b, we are writing it as df. That's what differential element, a small elemental force with respect to small elemental charge we are considering. That's what df is equal to dq v cross b. So as it is, just we are taking differential. So what the heading is, force on a differential current element. Force on a differential current element. Because of that, we are taking a df is equal to dq v cross b. Okay, the physical element of charge consists of a large number of very small. Okay, what we are considering previously, we are considering large number of very small discrete charge occupying a volume. Okay, within a volume we are considering like a sand like a structure. Okay, small elemental of if you consider in your hand sand, okay, small particles are there, those are nothing but charges. Okay, together it will become a large amount of the charge. Okay, that's what small charge we are indicating dq, whole charge we are indicating it as q. Okay, although small is much larger than the average separation between the charges. The differential force is thus merely the sum of forces on the individual charges. Okay, what I am telling is, so if I consider this is a small charge, okay, one more charge is there, one more charge, one more charge. So like this, too many charges are here. Okay, if you consider the diagram here, so these are the too many charges are there. Okay, if you see this, too many charges are there. So what is the total charge? Total charge is nothing but sum of these all charges. What is the total charge? It is the sum of these all charges, dq1, dq2, dq2 is to q1, q2, q3. So if you consider, so total charge will be all sum. Okay, the differential force is thus merely the sum of the forces. What is actually f is equal to? So with respect to each charge, what is actually force? Okay, together if you write like with respect to q1, f1, with respect to q2, f2, like that, f1, f2, f3, f4. So together you will be getting it as total f. Okay, that's what the differential force is, thus merely the sum of forces on individual charges. Okay, so this is what the example, gravitational force. Okay, just now I told the small volume taken in a shower falling sand. Okay, if you take a sand and if you leave that with respect to particular height, it will be falling. Okay, the small volume contains a large number of sand grains. Okay, small dust if you consider with respect to sand. Okay, those are nothing but a small number of charges. Okay, together it will be total force, total sand it will become. Okay, the differential force is the sum of forces on the individual grains. Sum of forces with respect to individual grain. With respect to first grain, what is the force? Second grain, what is the force? Third grain, what is the force? So like that, if we add all together, so it will become a total volume. Okay, with respect to volume, small volume will be considering. Within a conductor, electrons are motion throughout the region. Okay, if you consider a conductor, electrons are keep on moving. Okay, so with respect to immobile positive ions, which form a crystalline array. Immobile positive ions which form a crystalline array, giving the conductor its solid properties. Okay, this is what positive ions which form a crystalline array, giving the conductor its solid properties. A magnetic field which exerts force on electrons tends to cause them to shift position slightly. Okay, so whatever this magnetic field is there, because of this, those positive ions will be little bit shift. Okay, not too much. Okay, small amount of that. A small amount it will be shifting from its position. Okay, not fully moving from one place to other. Okay, it will be shifting always with respect to small position. So and produces a small displacement between the centers of the gravity of the positive and the negative charge. Okay, little bit displacement is there. That's what always you have to indicate it as a small displacement. Because of the magnetic field it is not a large displacement. Because of the electric field the displacement will be much high, but with respect to the magnetic field it will be small. Okay, the Coulomb force between the electrons and positive ions however tend to resist such a displacement. Any attempt to move the electrons therefore results in an attractive force between electrons and the positive ions of the crystalline lattice. Okay, the magnetic force is thus transferred to crystalline lattice and or conductor itself. The Coulomb force are so much great, okay, so much great than the magnetic force in a good conductor that actual displacement of electrons is almost immeasurable. Okay, so actual charge, whatever the sorry, uh, whatever the because of magnetic field and because of the Coulomb charge. Okay, with respect to the Coulomb force is much greater compared to the magnetic force that what we are indicating here. The charge separation that does result, okay, the charge separation that does result, however, is disclosed by presence of slight potential difference across the conductor sample in a direction perpendicular to both the magnetic field and the velocity of the charge. So you can observe here, this is what the movement, okay, current is moving like this, current is moving like this. Okay, the positive charges are there. Okay, because of the positive charge the electrons will be moving in this direction perpendicular and positive charges will be moving in this direction. Okay, if you consider the electric field is there, okay, whatever the electric field is there with respect to diagram B, if electrons are coming like this, okay, in that condition the positive ions it will be going upward and negative it will be going to the right hand side. Okay, this is what the called as a Hall effect. Okay, Hall effect or the whatever the voltage we are getting, it is a Hall voltage. The charge separation that does result, however, is disclosed by the presence of slight potential difference across the conductor sample in a direction perpendicular to both magnetic field and the velocity of the charge. The voltage is known as a Hall voltage and the effect itself is called as a Hall effect. So because of the magnetic and Coulomb charge together, so together whatever the displacement is there that we are in, indicating here. Okay, figure A, V is in a minus AX direction. Okay, V is in a minus AX direction. This what a minus AX direction. V cross B is in the AY direction. Okay, V cross B is in AY direction. AY direction is this one. Q is positive. Okay, Q is positive. These are the positive charges we are indicating. causing FQ be in the AY direction. FQ be in the AY direction. That's what positive charges, it will be going with respect to AY direction. Thus, positive charge moves to the right. Okay, with respect to second condition, reverse one, V is in the AX direction. Here it is a minus AX direction. Here it is a AX direction, positive AX direction. B is still in the AX direction. Okay, B is V cross B. That's what, not B. V cross B is in the AX direction. V cross B is with respect to minus AY direction. Sorry, minus AY direction. Q is negative. Okay, this is what we are indicating Q. This is what minus Q, minus Q, minus Q we are indicating. Minus Q. Q is negative. Thus, FQ is again in the AY direction. FQ is in again AY direction. Hence, negative charge end up with respect to right edge. Okay, negative charge will be ending up with respect to right side of the edge. We define convection current density in terms of velocity of the volume, charge density. J is equal to rho V into V. Okay, J is equal to rho V into V element. J is equal to rho V into V. Okay, that's what charge density. Okay, charge density is equal to rho V into V. V is nothing but velocity, rho is nothing but total charge with respect to volume. The differential element of charge may also be expressed in terms of volume charge density. That's what dq is equal to rho v into dv. Okay, so already in the previous chapters we have seen what is actually q in terms of volume charge. Okay, so dq is equal to rho v into dv. Okay, rho v into dv. So what we can write, df is equal to dq into v cross b. Okay, what we can write, what is actually df is equal to differential force. df is equal to what we have written already. So df is equal to dq into v cross b. E cross d element, v cross b. So that dq, what is actually dq here? So this dq is nothing but rho v into dv. dq is nothing but rho v into dv. So because of that, we are writing here rho v into dv into v cross b. Rho v into dv with respect to v cross b. Okay. So what is actually j is equal to rho v into v? Okay. What is j is equal to rho v into v? What we can write? So this is rho v. Okay. This is rho v, and this is what v. This is what v. So if you to combine together, it will become j. What I can write? J cross b into dv. So we are rearranging this expression. What is df is equal to? df is equal to j cross b into dv. J cross b into dv. So this is about the differential force with respect to current density. Okay, J is a current density, B is a magnetic field. Okay, dv volume. Okay, small volume charge. J into dv may be interpreted as a differential current. Okay, differential current element. So J into dv we can write it as a k into ds, that is equal to I into dl. So now we are converting our volume charge into line charge. Okay, we are converting our volume charge into line charge. J into dv may be interpreted as a differential current element. Okay, we are indicating it as a current element. With respect to current element, what I can write, current element with respect to the conductor of line charge, I into dl. Okay, with respect to surface charge, what I can write, k into ds. Okay, so thus Lorentz force equation. Okay, Lorentz force equation may be applied to surface current. Okay, Lorentz force equation may be applied to the current density. df is equal to k cross b into ds. K cross b into ds. So this is what the Lorentz force equation just now we have seen. A second. Okay, this is what the Lorentz force equation. Okay, force equation. This is what the Lorentz force equation. F is equal to Q into E plus V cross B. Okay, here we are taking it as a df. Okay, here we are taking it as a df. Okay, df is equal to K into B cross ds. Okay, K cross B into ds. Now, differential current element. Okay, because of current I dl cross B. Okay, I dl cross B together. Okay, so with respect to volume charge, F is equal to, if you integrate, okay, if you integrate This one. This one, df is equal to j cross b into dv is there. Okay, what I can write, f is equal to integration of volume j cross b into dv. Okay, with respect to surface, this equation, with respect to surface, if you integrate this, f is equal to integration of this df is become f, integration of this into kb into ds. Okay, surface charge is there, that's why we are indicating surface here. Okay, so f is equal to integration of df will become f, integration of s k cross b into ds. The third equation is this one. If you integrate with respect to line charge, okay, f is equal to closed surface integral I dl cross b, I dl cross b. Okay, this is what the condition. Okay, these are the three equations. Okay, one we are seeing with respect to volume charge. Okay, this is indicating volume charge. Okay, this is indicating a surface charge, and this is indicating a line charge. This is indicating a line charge. Okay, so three equations we are having. What is actually f is equal to? What is actually f is equal to? Okay, so applying 3 or 6 to straight conductor. Okay, so applying 3. Okay, equation number 3 is a line charge. Okay, this 6 is also for the line charge. Okay, for the straight conductor of uniform magnetic field. Okay, if you consider with respect to uniform magnetic field, f will become I L cross B. F will become I L cross B. This is for the only for line charge. This equation is only for the line charge. Okay. The magnitude of force is given with respect to familiar equation BIL with respect to sine theta. So if it is magnetic field and whatever the charge is making with respect to theta angle difference, so in that condition we are indicating it as a sine theta. Okay, theta, what is actually theta? Theta is the angle between the vector representing the direction of current flow. Okay, with respect to current flow and the direction of the magnetic flux density. Okay, two elements are there. One is current is there. Okay, this is what it is indicating with respect to I, and another one is, if you consider like this magnetic field lines are there. Okay, magnetic field lines are there. So together, okay, this is about current. Current is moving in this direction, and magnetic flux, okay, it is moving in this direction. Together, whatever it is making an angle, okay, this is called as a theta. This is called as a theta. So that theta we are indicating here. Okay, this is what the example. Okay, so one of the problem, as a numerical example of these equation, consider figure below. We have a square loop wire. Okay, in the z is equal to 0 plane. Okay, it is there on z is equal to 0 plane, carrying 2 milliampere of the field on infinite filament of y-axis. Okay, 2 milliampere of current is there with respect to this whole whatever the line. We desire a total force. What is actually a total force we are indicating? Okay, we have to calculate. Okay, this is what h is equal to, b is equal to, f is equal to. Okay, we have to equate this. Okay, so what is actually f is equal to? First we'll see what is the equation with respect to line charge. Okay, this is what about line charge. Okay, together. Okay, one of the line is here to here. Another line is this one. Okay, third line, fourth line. So total 4 lines we have to add. For that, what is the equation? F is equal to closure surface integral I B cross dl, or you can write it as minus I closed into surface integral B cross dl. Okay, so any one equation you can write. For that, what we require? We require B. What is actually B is equal to, and we require what is actually I is equal. So, and we require what is dl. Okay, we require what is actually dl also. Okay, so these three elements are required. What is actually I they are given. Okay, what is the I is equal to? I is equal to 2 milliampere. Okay, I is equal to 2 milliampere. So that is what the given thing. Okay, so we are writing here 2 into 10 raised to minus 3. We are writing 2 into 10 raised to minus 3. Now we have to calculate what is actually B. Okay, B we can calculate with respect to B is equal to mu naught into H. Okay, previous whatever the chapter we have seen, what is B and H relationship. Okay, we can write H is equal to B divided by mu naught, or we can write B is equal to mu naught into H. Okay, any expression you can write alternative. So here we can find what's actually H with respect to line charge. H is equal to I divided by 2 pi x into AZ. Okay, 2 pi x into AZ because of the AZ direction. Okay, magnetic field will be there with respect to AZ direction. Okay, that's why we are taking here AZ. That's why we are taking here AZ. So this what the field current is there. Current is moving like this. If current is moving like this, the magnetic field will be like this. Okay, it will be keep on rotating like this. Okay, it will be keep on rotating. So this is what the field, magnetic field direction. This is what the magnetic field direction. So with respect to that, we are indicating AZ component. I divided by 2 pi x. What is the I? I is equal to 15. I is equal to 15 ampere. So you can see here, this is what the current. Okay, so here one more current is there along y-axis. Okay, so this what 15 ampere current is there. 15 ampere current divided by 2 pi x. Okay, x you keep as it is into H. B is equal to mu naught into H. Mu naught is equal to 4 pi into 10 raised to minus 7 into H is nothing but divided by x we have to write. Okay, this what 15 divided by 2 pi. Pi will cancel out 2 with respect to 4. Okay, here it will be 2 into. Okay, so this what pi and pi will cancel out. This 2 will cancel out. 2 into 15 it will be 30. Okay, we can write it as 3 into 10 raised to minus 6 divided by x AZ with respect to t. Okay, so this what f is equal to, now will be coming, we have got what is actually I, what is B. Now we will be going with respect to dl. Okay, dl you can observe. Okay, first line if you consider dx into ax. Okay, second line if you consider dy with respect to ay. Third line if you consider, it will be dx with respect to ax. Fourth line if you consider, it will be dy with respect to ay only. Okay, dy with respect to ay. And what is actually x component? X component will see. Okay, one by one. Okay, x component will see one by one. Okay, in general this what the equation. In general this what the equation. I is nothing but minus 2 into 10 raised to minus 3 into closed surface integral of 3 into 10 raised to minus 6. This equation I'll be keeping here. That is what B, 3 into 10 raised to minus 6 divided by x AZ into dl as it is. Okay, now we'll equate what is actually dl. What is actually dl? So with respect to this line, okay, with respect to this line, it is along whatever the ax direction. Okay, positive ax direction. If you see this one, second line, okay, it is along positive ay direction. If you see third one, it is along minus ax direction. Minus ax direction. If you take the last one, it is along minus ay direction. Minus ay direction. Okay, so the x component here, it will be varying from 1 to 3. Okay, 1 to 3, it will be starting from 1 ending with respect to 3. So because of that, you can see here x is equal to 1, x is equal to 1 to 3, x is equal to 1 to 3, az divided by x. So remaining component, whatever the fixed elements are there, 3 into 10 raised to minus 6 we are taking outside of the integration. Az divided by x into dx into ax, into dx into ax. Okay, this was the first component. Okay, second component you can observe, second component what is varying, 3 to 3 it is same. Okay, 0 with respect to 2 you can observe. Okay, y value is here, starting value of y is 0, ending value of y is nothing but 2, ending value of y is nothing but 2. So because of that, what we are writing here, y is varying from 0 to 2, y is varying from 0 to 2. Remaining component az divided by 3. Why we are written x is equal to 3? Because x is constant here, because x is constant here. So what are the values here? 3 0 0. What is the value here? 3, okay, comma 2, comma 0. These are the value with respect to this point. These are the value for this point. Okay, 3 and 3 if you consider x, okay, it will be constant for the second line. For the second line we have completed this line, we are completing this line. Okay, So this was the second line. For the second line, x is 3 constant. X is 3 constant. So because of that, Az divided by 3 we are writing. Az divided by 3 dy into ay, dy into ay plus the third component. Okay, third component, this was the line, third line. Okay, along ax direction with respect to minus. Okay, with respect to minus ax direction. Okay, along minus ax direction. Along minus ax direction is there. Okay, that's why Az divided by x, x is varying from, you can see here, here it is varying from 1 to 3, but at this place it is varying from 3 to 1. Okay, it is varying from 3 to 1. Az divided by x dx into ax, Az divided by x into dx into ax. Okay, this was the third component. Fourth component is this one. Okay, along minus ay direction, along minus ay direction. Okay, so with respect to ay direction, you can observe y is equal to 2 to 0. Okay, here y is nothing but 0 to 2 is there. At this place it will become 2 to 0. Okay, same thing, az divided by 1. Okay, now x is becoming 1, you can observe x is becoming 1 here, x is becoming 1 here. You can observe here x is 1. Okay, x is 1. Okay, along this straight line, along this straight line, x is constant. Okay, we are observing for the last line. Okay, fourth line. Okay, x is equal to 1. So because of that, we are putting here az divided by 1 into dy into ay, dy into ay. So now we have to integrate with respect to 1 by x with respect to dx is nothing but ln of x. Limits are 1 to 3. Limits are 1 to 3 with respect to ay. Az cross ax is nothing but ay. Okay, next one, with respect to az cross ay. Okay, az with respect to ay. Okay, this is what minus ax we are getting. This is 1 by 3 y 0 to 2. Okay, integration of the second component. Integration of third component. It is once again ln of x. Its limits are 3 to 1. Here 1 to 3 limits are there. Here 3 to 1 limits are there with respect to ay. With respect to ay, the last component y az by 1 is just 1. Okay, with respect to this az cross ay, this is what minus ax. Y, here limits are, at this place limits are 0 to 2, at this place limits are 2 to 0. Okay, so if we equate these all together, okay, you'll be getting f is equal to minus 8 ax nano newton. F is equal to minus 8 nano newton. Okay, this is about the problem with respect to force. What they given is one of the current is here. Okay, one more charge is here. Okay, because of the together electric field and this magnetic field together, what is happening? Okay, what is actually force we have to calculate. What is actually force we have to calculate. Okay, total 4 lines, f with respect to this, f with respect to this, f with respect to this, f with respect to this. So all 4 line we have to trace. All 4 line we have to trace. Okay, so this was the problem. Okay, so next thing we'll see in the next class. Okay, force between the differential current element we'll see in the next class.